Hi class, welcome to exercise 1I, where we're going to learn all about perpendicular and parallel lines. The examples and pre-learning for you in this class are example 25, which is deciding if lines are parallel or perpendicular, and the questions for you regarding this exercise are 1 and 2 in the new book and 4 in the old book. And then we'll look at example 26, where we'll be finding the equation of a parallel or perpendicular line. And the questions for you for this example are question 3 in the new book and question 5 in the old book. So this is our final exercise on graphing lines. Some of you will be happy just to learn the skills and apply them, and that's just fine. However, some of you may be math nuts like me and would like to understand why some of these things are true. So if you stick around to the end, you'll be able to get a special bonus proof of why some of the facts that we're learning today are true. There's also some bonus challenges, and I hope these will be fun for those of you who like maths challenges. Okay, let's get on to the introduction. Before we work with linear equations, let's define the key terms for this lesson. The first term is parallel lines, and let's go through our geometric understanding of what that is. So our basic understanding is that if two lines are parallel, if they run side by side, never getting further away from each other or closer. If we have two parallel lines and another line that crosses them both, then because they're parallel, they both make the same angle with the line, which we'll denote as A, and mark it in the graph. Because any angle made with a straight line is 180 degrees, like this, then if I add the angle B to the diagram, it's obvious that A plus B equals 180 degrees. This means that the co-interior angles that the parallel lines make with the other straight line add up to 180 degrees. This will be helpful later on when we think about gradients of parallel lines. It's also going to be helpful when we think about gradients of two parallel and a perpendicular line, which makes a perfect segue to perpendicular lines. And this will be a geometric look at perpendicular lines. Two lines are perpendicular if their intersection is 90 degrees. In other words, just like this diagram. And of course that box there means that we have a right angle. Now combining this with what we know about parallel lines, then if two lines are parallel, and if another line is perpendicular with one of the parallel lines, then it's perpendicular with both. So if we look at this diagram, this other co-interior angle must be 90 degrees so that the two angles sum to 180 degrees. And this is following the rule that we learnt before, which I may not have mentioned, is Euclid's parallel postulate. Euclid was an amazing man who lived a long time ago. I really do suggest you look him up if you get the chance. Okay, so now let's try and relate this to linear equations. If I were to draw a graph of y1 equals mx plus c, and mark in the x values 1, 2, and 3, and then mark in the points on the graph where x is 1, 2, or 3. And then if I was to make a table of the values of y1 equals mx plus c, when x is 1, y is going to equal m times 1 plus c, which is just m plus c. And when x is 2, well, it's 2 times m plus c, and 3 is 3 times m plus c. So let's close off that table. And now let's think about if I was to draw a line y2 that was parallel to y1 equals mx plus c. From our understanding of parallel lines, we would know that it's always going to have the same distance d from y1. If I was to draw that distance d from the points where x is equal to 1, 2, and 3, and then draw the line y2 that goes through each one of those points, it should be clear that these two lines have the same gradient, but let's just make a table to be sure. So for x values 1, 2, and 3, y2 at x equals 1 is going to equal what y1 does plus d. So that is m plus c plus d. And when x is 2, that's 2m plus c plus d. And when x is 3, That's 3m plus c plus d. And let's close that off as a table. So as we saw in our very first lesson on linear graphs, I can consider the gradient the difference between each value. So here we can see in the table for y1, we have a difference of m and a difference of m, and it's no surprises that the gradient here is m. If we look at the table for y2, the difference between m plus c plus d and 2m plus c plus d is also m. And the same for the next value. So clearly, y1 has gradient m and y2 has gradient m. So we now know that parallel lines will always have the same gradient. I'll leave it up to you if you want to think about how the parallel postulate affects rise over run, or in other words, the gradient. I don't think I'm going over the top to remind you that parallel lines always have the same gradient. So you need to remember that, you need to write that down, and I'll write that down again later on in this exercise. All right, let's move on to perpendicular lines. Now, to show what role the gradient plays for two perpendicular lines is much more complicated. If you stick around to the end, I will show you exactly why. There's a proof for it. But for those of you who don't want to get the proof, here are some clues on how the gradients relate in two perpendicular lines. So the lines y equals x and y equals minus x are perpendicular. And let me show you with OneNote. So if I select these two, I'm going to be able to graph both of them with OneNote, with the maths function. But first I need to fix it. Okay, so when you see the two equations with a comma in between them, if I select the action to plot in 2D, there you go. And now you can see these two lines here are perpendicular. For y equal to x, m1, its gradient, is equal to 1. And for y equal to negative x, its gradient, m2, is equal to minus 1. And m1 times m2 is equal to 1 times minus 1, which equals minus 1. And now if I was to draw the lines y equals 2x and y equals minus x on a half, and once again use the magic of OneNote and insert it on the page, you can see that these two lines are also perpendicular. So for y equals 2x, m1 is equal to 2. And for y equal to minus x on 2, its gradient m2 is equal to minus a half. And m1 times m2 is equal to 2 times a minus a half, which equals minus 1. Although that's not a rigorous proof, if you do hang around to the end, you will get one. However, you can take it as a rule that for two lines with y1 equal to m1x plus c and y2 equal to m2x plus d are perpendicular if m1 times m2 is equal to minus 1, and that's equivalent as saying that m2 is equal to 1 divided by m1. So let's check out what's going on with perpendicular and parallel lines in GeoGebra. Okay, have a look at these three lines here. The green and the red one are parallel to each other, and the blue one is perpendicular to those two. And that's shown with the right angle, which is a square angle here between them. Looking at the equations, you can see that the gradient is the same on the parallel lines, and the gradient of the blue one is minus x divided by that gradient. So in other words, minus 1 divided by that gradient. If I move the constant up and down for one of these graphs, you can see that it doesn't change whether they're parallel or perpendicular. Now if I move this constant m, then all of the lines rotate, but they still stay either perpendicular or parallel to each other. As always, the link to this applet is in OneNote and in the video description. You're welcome to follow the link and try it yourself. With any luck, you'll be as hooked on GeoGebra as I am. Anyhow, let's get back to the OneNote. Okay, that's the end of the introduction. So just remember the rule: if I multiply two gradients by each other and they equal minus 1, then they're perpendicular. If two lines have the same gradient, then they're parallel. Okay, I'll see you in the next section. In this section, we'll be inspecting some lines and deciding whether they're parallel or perpendicular. And before we go on with the example, let's just remember the rules. To know if they're parallel or perpendicular, you only need to inspect the gradient. And even though we've mentioned these rules a few times, it's worth writing it down again before we start this example. So for two lines, y1 equals m1x plus c, and y2 equals m2x plus d, if m1 equals m2, then they're parallel. If m1 times m2 is equal to minus 1, then they are perpendicular. Okay, with that in mind, let's do example 25, which asks us to decide if the following pairs of linear equations are parallel, perpendicular, or neither. Okay, in part A, the equations are y equals minus 3x minus 8 and y equals 1/3 x plus 1. If we look at the gradient of the blue equation, m1 is equal to minus 3. And if we look at the gradient of the green equation, m2 is equal to 1/3. So m1 is not equal to m2, so they are not parallel. If we multiply m1 by m2, then that equals minus 3 times 1/3, and that equals minus 1. So they are perpendicular. Okay, that was easy. Perpendicular, not parallel. Let's have a look at B, where the first equation is y equals 1/2 of x plus 2, and the second equation is given to us in a linear relation form, 2y minus x equals 5. So we'll need to do a little bit of algebra on the green equation to find out what its gradient is. So 2y is equal to x plus 5. And now dividing both sides by 2, we get y equals 1/2 of x plus 5 on 2. So the gradient in the blue one is equal to the gradient in the green one. So these two lines are parallel. Okay, finally we move on to C, where they're both given to us in a linear relation form. And the first one is 3x plus 2y equals minus 5. And the second one is x minus y equals 2. So let's do the algebra for the blue one. Subtracting 3x from both sides, I get 2y equals minus 3x minus 5. Dividing both sides by 2, I now get y equals minus 3 on 2x minus 5 on 2. So m1 equals minus 3 on 2. And for the green equation, if I subtract x from both sides, we get minus y equals minus x plus 2. And multiplying or dividing by minus 1 on both sides of this equation gives us y equals x plus 2. Sorry, I meant minus 2. So m2 is equal to 1. Now because m1 is not equal to m2, they are not parallel. And m1 times m2 is equal to minus 3 on 2 times 1, which obviously equals minus 3 on 2, and that's not equal to minus 1. So they're not perpendicular either. So this means it's neither perpendicular or parallel. Okay, it really is that easy. Just get the gradient and compare them. Are they the same? If so, they're parallel. If you multiply them together and they equal minus 1, then they're perpendicular. If neither of those facts are true, then it's neither. Okay, at this stage you should really pause the video, and if you have the new book, go on and do questions 1 and 2. And if you have the old book, do questions 4. Okay, I'm going to see you in the next section. In this section, we're going to find the equation of a parallel or perpendicular line. Now, being parallel or perpendicular to a line is all about direction. This means gradient. Then to make an equation pass through a particular point, going in a particular direction, you need to, 1, first figure out the direction of the line by finding the gradient using parallel and perpendicular rules, i.e. find m, and then 2, use the x and y values of the given point with the value of the gradient to figure out c, i.e. find c. Then we'll know what the equation y equals mx plus c is. If you think this sounds a lot like finding an equation from a graph, then you're right. It is just like that. For those of you who are confident with that, this will be a piece of cake. But let's put this to work with example 26, where we'll have to find the equation of lines like the one in part A, which is the line that is parallel to y equals minus 2x plus 7 and passes through the point 1, 9. Alright, so for y equals mx plus c, to be parallel to y equals minus 2x plus 7, we need m the gradient to be equal to minus 2. So therefore, our new y is going to equal minus 2x plus c. And to pass through the point 1, 9, then there must be a point where y is equal to 9, and that will be equal to the gradient times the x value 1, in other words minus 2 times 1, plus our c value. So I'm going to add 2 to both sides, so that means that c will be equal to 11. So therefore the equation that's parallel to y equals minus 2x plus 7 that passes through the point 1, 9 is y equals minus 2x plus 11. So I hope that was straightforward for you. But let's go on to part B, where we need to find a line that's perpendicular to y is equal to 3/4 of x minus 1 and passes through the point 3 minus 2. So because m1 equals 3/4, for a line to be perpendicular, we need to be minus 4 on 3, because that's equal to minus 1 divided by 3 on 4. And if you don't believe me, you can multiply 3/4 by minus 4 on 3, and you'll see that that equals minus 1. So we need some equation where y is going to equal minus 4 on 3x plus c to pass through the point 3 minus 2. So subbing in this x and y value with a y of minus 2, we need that to equal minus 4 on 3 times 3 plus c. And this will make it easy to figure out what our c is. So minus 4 on 3 times 3 is equal to minus 4. So minus 2 is equal to minus 4 plus c. And adding 4 to both sides, then c is equal to 2. So the equation that's perpendicular to y equals 3/4 of x minus 1 and passes through the point 3, 2 is y is equal to minus 4 on 3x plus 2. Okay, I thought that was pretty straightforward as well. Hopefully you do too. So the final part of your pre-learning is for you to do question 3 in the new book and question 5 in the old book. And by all means, you can leave this lesson at this point. If you're working hard to understand the skills, then you should be proud of yourself. However, if you're a maths nut like me, then stick around for some knowledge treats and some fun challenges. And then I'll see you in the bonus section. Okay, welcome to this bonus section where we're going to prove the rule about the gradients of perpendicular lines. So congratulations on attempting this. I can well and truly say to you, welcome to the dark side. But I do have to apologise, we don't have any cookies. It was a lie. But we do have secret knowledge and lots of fun. So let's get on to this proof. Here we have two parallel lines, and the pink line has a gradient of m, and the blue line has a gradient of L. So if I draw a horizontal line that runs through the origin and then draw two vertical lines, and I'll be able to use these lines to describe the gradient in a much more tangible way. So first I'll need to name these points A, B, C, and D. And because L is the gradient of this blue line, then L has to equal rise over run, and this segment A to B is the rise. In this segment B to O is the run. So L is equal to A to B divided by B to O, where you can think of A to B as the segment length. Okay, and now to move on to M, which is equal to its rise and run. And its rise is this segment length here, but the negative value because we're traveling down. So that's equal to minus CD. And its run is this segment length here, which is equal to O to C. Okay, if you think you can solve it now, pause the video and have a go yourself and come back and see what I've done. Otherwise, let's keep on going. Now, because these lines are perpendicular, this angle here is 90 degrees. So if I mark in this angle here as X and this angle here as Y, then X degrees plus Y degrees plus 90 degrees has to equal 180 degrees because it's going along that line there. So this means that X plus Y is actually equal to 90 degrees. Now if we go back and look at these triangles, these are right angle triangles, and because X plus Y is equal to 90 degrees, this angle here must be Y, and this angle here must be X. That means I can redraw these triangles by rotating or flipping them. If I put the triangle on the right here, then this angle is X and this angle is Y. And just so you're totally clear on what triangle I'm talking about, I'll mark in the corners. So this is O, and this is C, and this is D. Therefore the other triangle is, and its corners are noted as. So I'm just going to transfer the values of L and M to here because I'm going to move this up and do some trigonometry. So hopefully you're confident with some trigonometry. Because X is the same angle in both of them, tan of X is equal to opposite over adjacent. And in this case, that's equal to the length of C to D over the length of O to C. And on the other triangle, tan of X is equal to B to O divided by A to B. So because they're equal to the same thing, that means that CD on OC is equal to BO on AB. So if I manipulate these fractions one more time, OC divided by CD is equal to AB divided by BO. So let's keep that in mind as I move over to the gradients. So M is equal to CD minus OC. So if I divide the numerator and the denominator by CD, I now have M is equal to minus 1 divided by OC divided by CD. And if we look back over at the other fractions, OC divided by CD is actually equal to AB divided by BO, which is equal to L. That means that M is equal to minus 1 divided by L. And if I multiply both sides by L, then we have M times L equals minus 1. Isn't that cool? So who knew we'd get trigonometry into linear relations? So if you've paid attention to that and you still don't understand it, I'm happy to talk about that in class to you. But let's move on to the challenges. Okay, challenge number 1 is involving this graph here. So the questions are, what is the gradient of y equals 3? And as x equals 3 is perpendicular to y equals 3, then the gradient of x equals 3, which we'll call m2, must be equal to minus 1 divided by m1, which is the gradient of the other line. So what is m2? Okay, now I'm going to move on to challenge 2. So challenge 1 is a question about logic, but this one requires a more mathematical approach. I've drawn this box here, and every angle here is 90 degrees. So these blue lines are parallel and these pink lines are parallel, and the blue lines are perpendicular to the pink lines. I'm going to say that this length here is 10 and this length here is 5. So my challenge to you is to tell me, if I name this point here B, what is the value of B? And if I name this point A, then what is the value of A? And if this point here is A equal to x1, y1, and this point here is B equal to x2, y2, what is the value of A? And what is the value of B? Hopefully the colouring makes it clear that we're talking about different things. And my final question is, what are the equations of these lines? So if you have the predilection and can find the time, go ahead, try these challenges. I totally recommend it. They're very rewarding. Let's keep up the good work and I'll see you all in class.